the Laplace transform of the derivative of g, the first derivative, the Laplace transform of g prime or Laplace transform of g of t. Remember, we're assuming that this little g function is differential, which means that it's continuous and it has at least first derivative well defined. So let's compute the Laplace transform of the first derivative of g. This means that we're doing the calculation of fancy L for Laplace of g prime of t. So we think now of the first derivative, dg dt or g prime, as an input function of the Laplace transform, which means that this is equal to integral 0 to infinity e to the minus st times g prime of t dt. This is simply invoking the definition of Laplace transform. Something sweet, however, is just about to happen because we now have that g prime as an argument of an integral. So we could also invoke the fundamental theorem of calculus, but we will. But let's first take a look at this with an experienced eye of a student of mathematics, certainly a student of differential equations, formerly a student of calculus 2 and calculus 1. So immediately you see this and you recognize this looks like u and this looks like dv. So we want to think of this as something that resembles integration by parts. So it could go as uv minus v du. Of course, we have to do the evaluation from 0 to infinity, but roughly speaking, this is what it looks like, right? So let's make a pause here, and in some bubble thought fashion, if you will. So I'm going to say u is the exponential e to the minus st. So du would be minus s e to the minus st dt. That'd be u and du. And then we think of dv as g prime t dt. This is the part where you integrate dv, then you would be using fundamental theorem of calculus, right? So v would be exactly equal to g of t. We close this bubble because this is the bubble thought in our head, right? That's how we're going to nail down the definition of Laplace transform of the first derivative, that function g. So we multiply u times v. So now we continue. Dot, dot, dot. U times v would be e to the minus st times g of t minus integral of v du, which would be minus s e to the minus st dt, and then v here would be g of t. And we're doing everything here from 0 to infinity. So 0 to infinity. This is also evaluated from 0 to infinity. We're going to pull that negative s. See, that integral has negative in the integrand of the integral. There's a negative s. We can pull that. We're integrating that integral with respect to t. So s is a variable, but for effects of that calculation, you can pull that s, right? And so negative s with that negative there, this becomes plus. So we could write this as s times integral 0 to infinity e to the minus st g of t dt. here we still have e to the minus st g of t from 0 to infinity. Now, so far so good, right? So we have, we started with the definition of Laplace transform. We took a look at this in terms of integration by parts. Along the way, we used fundamental theorem of calculus, and we're up to this stage. Now what we'd like to see, we'd like to do is we'd like to think of this here as the Laplace transform. This here is going to be the Laplace transform of the function g. That's exactly the definition of Laplace transform. So this is now looking, this would be equal to e to the minus st g of t evaluated from 0 to infinity plus s times Laplace transform of g of t. Now I have to do something about this evaluation, right? So the evaluation from 0 to infinity, let's work on that now. This is the same as saying, hey, let's take this from, say, minus st g of t from 0 to b, and then let's take the limit as b goes to infinity. This is equal to which means that this becomes limit e to the minus st, say e to the minus sb g of b minus this evaluated at 0. So this would be evaluated at 0. It's looking like e to the 0 g of 0. This would also take the limit, but, well, limit as b goes to infinity, as b goes to infinity, plus s Laplace of g. E to the 0 is 1, g to the g of 0 is 0. That doesn't depend on b. However, this other limit, that was the calculation we did initially, provided that g is of exponential order, right? So the calculation we did here said suppose g is differentiable and of differential order. So the limit, this limit, of course, here's in terms of t. If you substitute the t, another letter b, then you find the same type of limit. But that's what we would use to justify, look, this part here, this limit, this here is 0. Which leaves us with this being equal to minus g of 0 plus s Laplace transform of g of t. So in summary, so in so many words or so many symbols, we have found that the Laplace transform of g prime is equal to minus g of 0 plus s times Laplace transform of g of t. We could also write this right-hand side as minus little g of 0 plus S times big G of S. This is customary to use same letter, lowercase meaning the function on the time domain, uppercase meaning the function on the frequency domain. So this we could add this to the table. We had discussed last week the table of original functions and Laplace transforms. We can come up with a new table on its own. Let's say, so we could have something that looks like little f on the first column and Laplace transform of little f on the second column, this being big F. So we have the input being the derivative of a function, then the output becomes S and the Laplace transform of that function minus the original function evaluated at 0. If the input were not the first derivative, excuse me, but rather the second derivative, okay, doing similar or consistent steps, similar to the steps we just did, carried out, then this becomes a square Laplace transform of that function minus S G, the function at 0, minus G prime of 0. Remember that for second order problems, G prime, the derivative, the first order derivative, is part of the initial conditions, right? And so you could also have something in terms of derivative of order 3. So you have the third derivative of little g, then you get here an expression that looks, I guess the pattern we want to see on the second column is a pattern of polynomials in terms of the variable on the frequency domain, right? So order 1, meaning first derivative of g, gives you something linear in S on the frequency domain. Order 2, derivative of order 2 on the time domain gives you a polynomial of degree 2, a quadratic polynomial on S, which is defined in the frequency domain. Derivative of order 3 gives something that looks like S3 big G of S minus S square G of 0 minus S G prime of 0 minus G double prime of 0. So it kind of, for this last one, it goes S3, S square, S1, and S to the 0. Right? So it's kind of like a polynomial on the variable on the frequency domain. And so the moral of the story being is that we want to transform the original problem, which is a derivative on time domain, into a problem that looks more like a polynomial on the frequency domain. And so finding the solution G here is going to be something that relates to solving for the Laplace transform, that function on the frequency domain, which is what is referred to as the algebraic problem.